Hi Year 12. This lesson is all about total internal reflection. It is 13.3 in your book on page 193. What I want you to be able to do is state conditions for total internal reflection, calculate the critical angle from the refractive index, and then describe the structure of an optical fibre and cladding, or the function of the cladding, and then in terms of multiply dispersion, why the core of an optical fibre is narrow, and describe how optical fibres are used in communication. I might have to make the video in two parts, so see how we get on time-wise. So, what we've done in the lab is you've got a semicircular glass block out, and you put a ray of light going in, and you can see the light being refracted as it comes from glass going to air. It goes straight along here because it's going along the normal. We've seen before, it won't change direction. Now we're interested in looking at this angle of instance when the light goes from glass going back to air. Now, guess what I've got for you is I've got a wonderful simulation that'll let you do the practical. Now, I'll put the link on Edmodo. Here's going to be a semicircular glass block, and here's going to be your laser beam going in. Now you can see here, again, from going from glass to air, it's going to bend away from the normal. What you can do, and this is very exciting, even Danny will be excited by this, is you can take your protractor and put it just here, and what you're able to do now is measure the angle of refraction as it goes from the glass going to the air. I think along there, more or less have. Anyway, as you can see here, the angle is going to be 10, it's about 13, 14 degrees, the angle of instance. And you could put the protractor here to measure the angle of refraction, but you did that in the previous lessons, so we're not going to do it this time. What I want you to notice is, as I make the angle of instance bigger, you can see it going straight along here, when I get to about 40 degrees, about here, can you now start to see some reflection happening? Now this is a bit weird because light now is refracting and reflecting at the same time. Again, the true explanation why this happens will come to quantum physics, but again, luckily that's not part of the A-level syllabus. But what I want you to see is a little bit of reflection happening, he says as he starts coughing away. Now, as I make the angle bigger and go back here to about 10, 20, 30, 40 to 45 degrees, can you see now the light is completely reflected? This is acting like a mirror now, and this is called total internal reflection, TIR. But there's this very special angle about here, about 42 degrees. You get it about right about there-ish, where you can start to see the light more or less goes completely along here before you get total TIR. Now, when the light goes along the base here, we call that the critical angle. And what I've got you to do in the lab is do that experiment. Now, these are the pictures from your book. This first one here is when you've got the angle of instance is less than the critical angle, and you get your refraction and a little bit of reflection. The next picture in your book is where you bang on the critical angle, and now the light goes along here, and now it goes along the base here, and you get that reflection, and there is your critical angle, normally the symbol uses IC. Then, when you go above the critical angle here, so now I've got an angle of instance greater than the critical angle, now you've got your total internal reflection. This is really, really useful, and you've got loads of applications I'll show you soon in optical fibers. Now, for the state the conditions for total internal reflection, and this is important, you've got a refractive index N1 and N2. Now, for this to happen and get total internal reflection, you must have N1 must be greater than N2. For example, if you've got glass here, the refractive index is going to be 1 for glass, and then for air is 1. 1.5 is greater than 1. And you always got to have that because you've got to bend away from the normal. And the second part, as they like for this, conditions for total internal reflection, is your angle of instance has got to be greater than that critical angle. So the two things you have is you must have N1 greater than N2, and you must have the angle of instance greater than the critical angle. Now, getting back to this lovely little equation here, when we had sine 1 sine I is then equal to N2 sine R. If you've got the critical angle just here, can you see your angle of refraction is equal to 90 degrees? So going back here, that must mean you've got sine 90 here. Now, this equation then changes, and now we're going to have the critical angle, because I've got now angle refraction going to be 90, and we all know now that sine 90, whoops, get that right, is going to be 1. Hence, if you go through your algebra, that happens. Sine critical angle is N2 over N1. Now, going to different color pen, if you got the case of glass, is that then the sine of the critical angle, well, for glass, we're going from into air, so your N2 is 1. Glass which you're traveling through, the N1 is going to be 1.5, and you bung that into your calculator, you find that equals 0.6. And if you inverse sine it, I think you probably find is about 41.9 degrees, which is 42 degrees roughly. That tells you the critical angle. It's a very, very quick way of doing it. There's nothing new. All you're doing is taking that equation and you're doing sine 90, which ends up being 1. You shouldn't have to memorize that to work it out. Now, this is an interesting one. All of us at home have a very expensive diamond, don't we? No. So when you look at a diamond and you see it twinkling like this, it's really, really interesting, because the reason why it twinkles, because diamond refractive index is 2.417. So when light enters your diamond here, if you go back to your equation you got before, where you have your sine of your critical angle, and the equation we had before, remember, was your N2 over your N1. Once the light goes in here, is obviously then going, that's going to be 1 over 2.417. When you calculate the critical angle, I think you find it's about 24 degrees. What that means then, as light's trying to get out of the diamond, well, a lot of the times you're going to find it's going to be greater than 24 degrees. So what starts to happen is you get TIR. Therefore, the light gets trapped inside the diamond. It can't escape because you've got total internal reflection. Now, why you see these colors coming out? Well, exactly what you've seen before. If you have light coming in, and it's not perfect rectangle shape, it's like a little pyramid shape. When the light comes in here, you get the different colors out of red all the way through, red, orange, yellow, green, blue, indigo, and violet, way through like this. You get different colors are going to be refracted by a different amount. Now, if you've got total internal reflection happening over and over and over again, the colors get separate further and further and further. Hence, when the light eventually does come out, you start seeing the red, orange, yellow, green, blue, indigo, and violet, which you start seeing here. And this is the sort of question we're starting to find in the exams now, where they're making you think. And it could be, using the fact diamond's got a refractive index 2.417, explain why you start to see the colors. Now, I'm going to stop this here, and the next part of the video is going to be about optical fibers.